Welcome to Physics 2425, Lecture 11 on oscillations. So we're going to be taking a look at cases in which we have an object that is oscillating back and forth. This is going to include mass spring systems, pendulums. Pendulums are different shapes. It could be a ball on a string, or it could be a rod that is swinging back and forth. But that is the goal for this particular lesson. So in general, we are talking about periodic motion. Periodic motion is motion that returns to a given position after a fixed time interval. There are lots of different types of periodic motion that you might have, but we're going to be looking most specifically at simple harmonic motion. So simple harmonic motion will abbreviate as SHM to save time. And it is a special case of the periodic motion in which the magnitude of the force is proportional to displacement, which means the bigger the force, the bigger the displacement, and vice versa, but is in the opposite direction. So remember, the negative here is going to imply opposite direction. So an example that is periodic but not simple harmonic motion would be a elastic bouncing ball. So let's picture we had a purely elastic situation where you drop a ball from a height of h, and because it's elastic in our no energy loss sense of elastic, it's going to be able to bounce back up and down, returning the same height over time because it's not losing energy with the bounce. So we have to think about the force that is causing the displacement. In this case, that force would be the gravitational force. So if I picture the ball here on the way down, gravitational force would act down. That gravitational force has a value equal to mg. So because the gravitational force is not dependent on the height, which would be the displacement above the ground or the displacement from any point in time or location, then that first condition, the force is proportional to displacement, is not true. Additionally, if you look at the direction of force, on the way down, the gravitational force and the displacement are in the same direction. But on the way up, they are in the opposite direction. So because it's not true that they are always in opposite directions, then therefore not simple harmonic motion. So even if we could have that elastic bouncing ball, it is not simple harmonic motion. It's simply periodic motion. So when we look at simple harmonic motion, the two main cases that we are going to see is going to be the mass spring system, for example, that we have demonstrated here. So we can take a look and see why this is considered simple harmonic motion. So we usually set in an oscillating mass spring system the x equals 0 to be the point where the spring is unstretched. So that means it's never stretched or compressed at this instant in time. So what we're going to do is we're going to pull the mass back, and we are going to let it go. So at the instant shown, we are no longer holding on to the mass. All that is affecting our mass right now is going to be the spring. We're going to assume that our surface is frictionless, so that way we're not worrying about friction in this case. We can actually see what happens when we add a friction force in later. So our force that's going to be acting on our block is going to be gravity and normal force, but those are vertical and those are going to cancel out. So what we really have here is we have a spring force, and we can see that that spring force is going to be acting in the opposite direction of the displacement, which is going to force the object to move back towards the center. So as the block moves back towards the center, when it has a displacement of 0, the force is 0. When it moves past the center, the spring force is now going to change directions as the spring is compressed. And what ends up happening is our displacement is now going to be to the left, but our spring force is going to be the right. So we can see here that our spring force is always going to be in the opposite direction of displacement. And because we know Hooke's law, which says that our spring force is equal to negative kx, we can see that the magnitude of the spring force is proportional to the displacement. So the larger the displacement, the larger the spring force. And we can also see that the reason we have that negative there is because we know that our spring force is also always in the opposite direction of displacement. So that makes our mass spring system oscillating an example of simple harmonic motion. All right, so we're going to look at a mass spring system here. Now this one's a little different than the horizontal situation that we were looking at. So in our horizontal situation, we had our spring and our block. We had a gravitational force, a normal force, and then it was our spring force that was in the opposite direction of our displacement from whatever the equilibrium position was. And that spring force was the driving force behind the oscillation. We were assuming there was a frictionless system. Well, in this case, we actually have both a gravitational force and a spring force that is acting. And we're going to ignore any sort of dampening forces like friction with the spring or anything like that. So we're going to have our gravitational force coming down, and our spring force is actually pointing up here at this instant. Now the instant shown is the equilibrium position where these forces are equal to each other. So the reason my spring force is pointed up is because my displacement from the natural resting length of the spring right here is upward. So we have an upward spring force. And what I'm going to do is I'm actually going to give this thing a vertical displacement up from that equilibrium position. To that instant, not quite where we're there, but where we still have that upward spring force. We're going to give it a little displacement above that equilibrium position. And then I'm going to hit play. We're going to see what happens. So you can see that that gravitational force vector is always constant, but my spring force vector is getting larger and smaller. Now this would work if I actually had lifted this up above as well. I just think it's a little cleaner here not to have to worry about the change in direction of the spring force. So my spring force is getting larger and smaller, yet my oscillation is being centered directly on the equilibrium line. So I'm going to have some sort of displacement that is going to be up and down away from that. And I can see that my gravitational force is always constant. My spring force, though, is changing in magnitude. But if I were to redefine x equals 0 for my spring force, which I cannot actually do here, I don't believe I can do that with this particular simulation. But if I could, if I was to measure my spring force relative to that equilibrium position, I would find that my spring force would equal negative kx, where x equals 0 is the equilibrium position of this oscillation. And that the fact that the gravitational force is there doesn't actually matter. And I believe I can see that if I were to turn off my forces here and turn on my net force. And if you look at my net force is changing directions. And in this case, my spring force is equal to my net force, because at equilibrium, my spring force is equal to mg. So effectively, my gravitational force has already been taken care of in the initial stretch of the spring. And that's really all that gravitational force is doing. Now you could do a mathematical derivation to prove that the spring force, assuming that x equals 0 is the equilibrium position, does give you a value that is equal to your net force, and you can show that the gravitational force cancels out, but that is not strictly necessary for our understanding of the oscillation. The purpose of this is just to kind of bring to the forefront that the gravitational force is not actually causing the oscillation. The gravitational force is causing the initial stretch of the spring. It is still always acting, but what is causing the oscillation is the displacement of the spring relative to that equilibrium position. All right, so let's work on our definitions a little bit more. So Hooke's law defines that our spring force is equal to negative kx. So in simple harmonic motion, we define a force that is the restoring force. The restoring force is what is responsible for returning objects back to the equilibrium after displacement. So in both of the examples we saw with the spring, both the horizontal and the vertical, when you look at the equilibrium position, which horizontally is the unstretched location of the spring, whereas when you have the hanging system, that is going to be when your gravitational force is equal to your spring force. When you measure your displacement from whatever that equilibrium position is, that is going to be what we're going to call the restoring force. So in this case, it's the spring force. The restoring force must always point toward the equilibrium position. And it must be in the opposite direction of the displacement. And the magnitude of the restoring force is always proportional to the magnitude of the displacement. So with the last two examples, we have shown that the spring force meets the requirements of the restoring force. But there are many other examples of simple harmonic motion. They do not all have to be mechanical. They could be related to like oscillations of electrons in terms of the electrostatic force. But for this example, we're looking at the springs and we will look at pendulums. But the definition of restoring force in simple harmonic motion works more in larger terms than just mechanics. Now, this is actually only going to work for like small ripple type waves, the ones that you see actually making oscillations. When you think of like a big ocean wave, there's a whole lot more going on with an ocean wave, such as the topography of the ground, and then also gravity is going to have a bigger impact. And then we start deviating from a simple harmonic motion model. So this is only going to work kind of like for the ripples that you might see on a pond. But this is an example where you do have a different type of restoring force than just the spring force. Now, all of simple harmonic motion kind of boils down to defining that oscillation. So mathematically, the net force in our cases is going to be the spring force. So in both the horizontal and the vertical case. So according to Newton's second law, our net force is equal to mass times acceleration. So in this case, we have negative kx is equal to m times a. But acceleration is the second derivative of position over time. So what you can do is you can substitute in d squared x dt squared for the acceleration. And when you do that, you get a differential equation. So different ways to write this. This is just using Newton's second law, subbing directly in. But more traditionally, when we're looking at the spring force, this differential equation is written like this. Okay, so your d squared x over dt squared is equal to negative k over m times x. And so basically the ratio of the spring constant to the mass is one of the defining factors of the oscillation. Because the mass is providing inertia, and that spring constant's kind of what's providing the resistance that's pulling back in. So this is our differential equation. Now, this is a second order differential equation. This is not something that you have probably seen in your math classes. This is definitely a higher level math. And solving this differential equation is not something you'd be expected to do. So we need to find a way to avoid solving a second order differential equation and still be able to describe the simple harmonic motion. So how are we going to come up with a solution to this? Well, our acceleration is not constant during the displacement. If we were to just go back and forget about the second order differential equation right now, if we just set our net force equal to mass times acceleration, we have negative kx equal to ma. So for example, if I was to graph that, this is what that graph would look like. It would have a slope of negative k, and if I have a positive x, then my slope is negative, and that is going to then cause my force to be in the opposite direction. Over here, well, I have negative values for acceleration. It wasn't really the slope is negative, but I have negative values for acceleration, positive values for displacement, so those are in opposite directions. Up here, I have a positive acceleration, but I have negative position. So once again, they're in opposite directions. So we can see this is supporting our oscillation. So if we were to take a look at kind of the maximum values, our maximum acceleration is going to occur at the amplitude of the oscillation. So if we were to look at kind of the amplitude of the oscillation that we're going to have, oscillations have amplitudes, so they go from positive to negative kind of with those oscillations. So we're going to have our maximum acceleration is going to be negative Ka over m. So we can see that our acceleration is very, very dependent on our displacement, because we are going to have a maximum value. We are going to have, it could be 0 and it can be anywhere in between. So what all of this means is that our kinematic equations are absolutely not valid, because our kinematic equations that we would use to relate position, velocity, and acceleration all assume that our acceleration is constant. So we cannot use kinematic equations. That second order differential equation is beyond the scope of this course. So how are we going to find x of t? How are we going to find a of t? How are we going to figure out what these values are over time? Well, we do have to go back to that differential equation. We cannot solve this on our own, but the general format of a second order differential equation is this. So we end up with d squared x over dt squared equaling negative omega squared times x. This is the standard format. So this actually works for any second order differential equation. So for any second order differential equation, this is true. So this works both for a pendulum. It will also work for our spring system. It would work for our electron system. So this is going to be something that we can solve. By comparing this to our second order differential equation found by using Newton's second law, we can find that the angular speed, which is what omega is, okay, that's our angular frequency, that's how often we can oscillate. Our angular frequency is 2 pi times our regular frequency. Our regular frequency is 1 over period. We saw those in circular motion and rotation. So our d squared x over dt squared is equal to negative omega squared x. So if we compare those, we get that negative omega squared x is equal to negative k over m times x. So that tells us that omega squared has to equal k over m. And therefore we can find that omega is equal to k square root of k over m. So this is going to tell us what our oscillation rate is going to be for this mass spring system. We can see that it is based both on the spring constant k and on the mass. Sometimes when we look at oscillation rates, it's easier to look at period, because period is the time it takes to complete one oscillation. So if we do a little rearranging, so our frequency f is going to be omega over 2 pi. So if I substitute that in here, omega over 2 pi, what I can see is that my period t, like cross multiply and divide there, is going to be equal to 2 pi over omega. So if I were then to make that substitution, I would do that my period is going to be 2 pi over the square root of k over m. We could also flip and multiply, and that's going to give us, for a spring, our period of oscillation is going to be 2 pi times the square root of m over k. And I really like this version better. Just kind of, it makes more sense in my head. This is what's more important in terms of the oscillation and looking at the differential equation, but trying to make sense of what this means. The period, the time it takes to complete one oscillation, is going to be directly proportional to the square root of m. So if I was to double the mass of the block that was attached to the spring, my period would be the square root of 2 times larger. So it's going to be larger, but not quite double. At the same time, the period of my spring is going to be proportional to basically 1 over the square root of k. So if I were to double my spring constant, make my spring stiffer, then what's going to happen is I'm going to end up with a smaller period. And so then I'm going to have a faster oscillation. That just kind of makes sense. So mass is kind of like our inertia. So we're going to have a slower oscillation. It's going to take longer to complete one oscillation with a larger mass because it's going to provide more inertia, more resistance. But if I have a larger K, I'm going to have a smaller period. That's because that spring constant is directly related to our spring force. Larger forces is going to give us a faster oscillation. But how did we know what this was? Well, that's the part that's kind of beyond the scope of the course. So we know now that our acceleration is dependent on K, M, and X. But we don't have functions for the position, velocity, and acceleration over time. So what mathematicians would have done to solve this problem is they would have come up with equations in their brain. They would have kind of looked at different functions, and they would have figured out what function would meet this requirement that d squared x over dt squared is equal to negative k over m times x. Well, what ends up happening is the powers that be figured this out. And they figured out that some sort of sine and cosine function could meet these requirements. So although I'm not going to show you how to solve this differential equation, I'm going to show you that the function that we are going to define for position of a oscillator over time is going to meet the requirements of this differential equation. If you are really good at math and you are really curious about what this is, you can look up videos to show how to solve the second order differential equation for a simple harmonic oscillator. I did it in grad school. It's actually really fun, but it requires advanced math. Otherwise, we're going to just skip on to the next page. So what the powers that be, the brilliant mathematicians and physicists found, is that we can define a function for x of t that meets this form. So x of t is going to be a. A is going to be our amplitude. Amplitude is our maximum displacement. So omega is that angular frequency. So we've defined that our angular frequency is the square root of k over m for a mass spring oscillator. This equation works for more than mass spring oscillators, but that's the one that we've looked at so far. So, and it gives you an angular frequency in radians per second. We're going to have time. Time needs to be in seconds. And then we're going to have this guy phi. And if you remember, you've looked at cosine and sine functions in pre-calculus and calculus courses before, most likely. But phi is our phase constant in radians. It represents a shift in the horizontal from a perfect sine or cosine function. Now, if you look at different textbooks, different websites, different tutorials will alternate between using a cosine function and using a sine function. Either are acceptable because both sine and cosine will meet the requirements to be solutions for the second order differential equation. I prefer using cosine. Cosine makes the most sense to me because if you look at a perfect cosine function with no phase variance would have your maximum amplitude, if this is x versus t, occurring at t equals 0. And that makes sense because usually what we do is, if this is like my equilibrium position, we pull back our object and we release them at t equals 0 from rest after having already been displaced. So it makes sense for a maximum displacement to occur at t equals 0. Now, in reality, if you were doing a physical lab, what we would do is we would use like a motion detector and say we were doing like the vertical system and we had a block here. So a common way to do this is to put a motion detector on the bottom and then basically give this guy a little displacement so it oscillates up and down. Well, if you turn the motion detector on and then wait to hear it do its motion detector clicks, you would get a kind of flat part before the oscillation would begin. and then you'd have to cut that out. So a lot of times what we do is we say, okay, let's displace it first, then start the motion detector so that it's already in motion. Well, if the motion detector doesn't start at t equals 0 whenever we're at a maximum, you are going to have a phase variance. And that's kind of what this graph is showing right here, is that there is going to be a phase shift. Now, when you have a positive here for phi, that represents that the graph has been shifted to the left. If you have a negative value for phi, that means it has been shifted to the right. Now, of course, sine and cosine only differ by a value of, they're offset by pi over 2. So all you have to do is shift your graph, and you can make, if our phase variance is high enough, we can make this look like a perfect sine function, which is why it doesn't really matter whether it's a cosine function or it's a sine function. And in terms of the physics, the actual phase variance that we have, the phase constant here, doesn't really give us any physical meaning in terms of the amplitude of the oscillation. It just changes kind of our position at any instant in time, but it doesn't change the amplitude, it does not change the frequency. So we've already got our equations here for period and so forth. So if you were looking at position versus time, period would be the time from crest to crest. Amplitude would be the distance from the equilibrium position. So you can have a positive amplitude, you can have a negative amplitude. So this function right here would describe our simple harmonic motion. So all simple harmonic motion can be described by a sine or cosine graph. So that's another kind of special case once we have gone through and solved our differential equation. Now, our definition of position is a cosine of omega t. Our definition for velocity over time, velocity is the rate of change of position over time, which is dx dt. So if you were to take x prime of t, what would end up happening is you would take a, because it's a constant, times the derivative of cosine, which is going to be equal to a negative sine of omega t plus phi, but we have to use the chain rule. So we are going to need to take the derivative of the inside. The derivative of the inside is just going to be times omega. So when you rearrange that, you get negative omega times a sine of omega t plus phi. So what ends up happening here is that because our velocity is the slope of the position graph, whenever we are at a maximum, our slope is 0, which means our velocity is 0. Whenever our position is 0, that is actually where our slope is going to be at a maximum. In this case, our slope is at a negative maximum. So we can see that we're at a negative maximum right here. Here again, we're going to be, here we're going to be 0 again, because our slope is 0. You can see we're at 0. And then we are going to have a value here that's going to be a positive max for velocity because we have a positive slope. And over again, that's going to oscillate. So we are going to have a maximum displacement or a minimum displacement when our velocity is 0. And that's if you think about from like an energy perspective. If we are oscillating back and forth between an equilibrium position, we are starting off with a speed of 0 when we're at rest, when our position is at a maximum. As our position decreases to x equals 0, we are going to be converting potential energy from the spring into kinetic energy. And so we're going to end up with a maximum velocity. In this case, we're moving to the left, so we're going to have a negative maximum. As we move past, our displacement is now going to increase again. We're gaining potential energy in the spring, which means we're going to be slowing down. That's also because our spring force is in the opposite direction. So that basically when we get to the x max again on the negative side, we are going to be back to v equals 0. So this oscillation is going to continue back and forth. So you can kind of think about this from an energy perspective. You can think about this from a position velocity acceleration, looking at the slopes. So if you did not know that this function was supposed to be a sine or a cosine, you could actually do the oscillation with the motion detector and you would get this graph. You could even do this by hand. You could look at a video and you could record positions and you would be able to find that this oscillation is described by either a sine or cosine function. So once we have our velocity, we know that our acceleration is the second derivative of position. So we would look at v prime of t. We would now have negative omega, and a is constants. The derivative of sine is cosine, so we'd have cosine of omega t plus phi, but we'd have to multiply by the inside again because of the chain rule. So we end up with our negative omega squared, a cosine of omega t plus phi. So when we take a look here at comparing our velocity and acceleration graphs, because our acceleration is the slope of the graph, here we have a negative maximum acceleration, which means our acceleration is pointing to the left, and that's going to be occurring because the slope right here of the velocity time graph is negative. And that's going to occur at the maximum value is going to occur whenever the velocity is 0. So when our velocity is 0, that's going to be on these outer edges when we're at the amplitude. When we're at the amplitude, remember that our spring force is going to be at a maximum, either a positive or a negative maximum at that case. And since our spring force is equal to mass times acceleration, that's also going to give us our maximum acceleration. So in this case, we are going to have our maximum acceleration in the negative direction when we switch from positive velocities to negative velocities. So that is going to occur over here on this edge because we were going this way. We come to rest and then we come back the opposite direction. So that gives us a negative maximum in acceleration. So our A max is going to be negative and going the next direction. So here our velocity is at a negative maximum. So we're going to have an acceleration of 0. That's going to happen whenever we are at a position of 0. So you can see that those line up as well. And you can continue here. You're going to be at your positive A max going this way. So you can see that our displacement is actually at a negative maximum whenever our acceleration's at a positive maximum. Because right here we have a negative position at a maximum. We have a positive acceleration. And that's going to be coming from the fact that we have the negative sign here with our acceleration. Now when we take a look at these, the general cosines here, A is our x max. So x of t is going to be x max cosine of omega t plus phi. Right here, v of t is going to be negative v max. And that's just going to be the magnitude of our maximum speed. So our maximum speed is going to be omega times the amplitude. And then here for our acceleration, our A max is going to be the magnitude of our maximum acceleration. We had actually already proved that one by looking at the net force equation. So that was actually something that we could have found before. So we have now the ability to kind of define position, velocity, and acceleration over time for any of our simple harmonic oscillators. So how do we know that these actually satisfy the differential equation? They look nice. The graphs make sense. If you were to look at a video of this where we collect data, you'd be able to see that these graphs make sense. So how did all this come out? How do we know that omega squared was equal to k over m? How do we know that these equations are still valid? So there's a lot of things going on here. So what we can do is for d squared x dt squared, that is the same thing as a. So we could plug in negative omega squared a cosine of omega t plus phi on the left side. We could also then on the right side sub in x of t, which is a cosine of omega t plus phi. So if we do that, and you can kind of compare, we can see that the cosine of omega t plus phi appears on both sides of the equation. So if we were to divide out, it would disappear, as well as the amplitude of the oscillation also would divide out. And the negatives would cancel. So we had negatives on both of those. And we'd be left with omega squared is equal to k over m. So once again, we had to know that this function would obey the differential equation. So mathematicians and physicists had to come up with that. That was actually a huge major discovery. But we can see and we can prove that once we know that x of t is a cosine of omega t plus phi, that it does satisfy our second order differential equation, we can therefore find the angular speed of the angular frequency of our oscillation, and therefore the period of our oscillation, using the differential equation that we have set up. So as we already talked about, this shows that omega is equal to square root of k over m, and then our period is 2 pi square root of m over k. So all of this is in order to be able to describe position, velocity, and acceleration over time, and then also to describe the rate at which the oscillation occurs, because we cannot use the kinematic equations because our acceleration changes over time. So what do we really mean by that phase angle? So here's an example of that. So looking a little bit more closely. So this is our perfect cosine function, which would give us a phase angle of 0. So this is our perfect sine function. So this would be a phase angle of negative pi over 2, because we can see that we have shifted our graph over by pi over 2. 1/4 cycle. So our second example is going to be the pendulum. So the simplest form of a pendulum would be just a point mass on the end of a string. So as we displace the point mass, we can see that we create an oscillation. Now, it may not be immediately obvious why this oscillation is simple harmonic rather than just periodic. And actually, it's only periodic when we have small angles. If our angle gets too big in real life, and also in the math as well, then this deviates from our assumptions of simple harmonic motion. So we do have to keep our pendulum moving at small angles. If it moves at larger angles, then it would not work quite to the same extent. So small angles, it comes up with slightly different definitions depending on what website you look at. I would say somewhere between about 15 and 20 degrees. I'd say once you go past about 30, you're definitely going to be getting into larger angles, and it would deviate a little bit further. But the reason this is a little more complicated than mass spring systems, first of all, we have circular motion, so that's always fun. And if you look at our velocities and our accelerations, things get a little bit interesting. Let's give it a little more displacement just so we can kind of see the simulation better. So the first thing you can see is that our velocity is staying kind of parallel to the path that is being formed. And that's because our velocity is essentially in the same direction as our displacement. And our displacement is going to be along that path. The weird thing is that our acceleration, which is related to our net force, is making this fun little oscillation. And that's because in our circular motion, we have a centripetal force and therefore a centripetal acceleration. But because our velocity isn't constant, that means we also have a tangential acceleration. So we kind of have to break this one down a little bit more in order to see why this pendulum actually meets the conditions for simple harmonic motion. Because we have two forces, we have tension and we have gravity. Gravity always points down, tension always points along the string. Neither of those really point in the opposite direction of the displacement, which would be the opposite direction of that little velocity vector. So this is kind of weird. What's going on here? All right, so we're going to be looking at here is the simple pendulum. So as mentioned, the tension and the gravitational forces are the two forces that are acting. Now, what we're going to do is we're going to look at very, very small parts of the displacement. So we're not going to look at the whole angular displacement theta here. That's actually our amplitude here, theta. We're going to assume that this is pulled back to an angle of theta. What we're going to assume is that in some small amount of time, our pendulum goes through some very, very, very small displacement. So if I picture that this is my starting displacement right here, that's my theta, what I'm going to be looking at is an instant in time in which I have gone such a small displacement that the arc there of the arc length of that path is going to be very, very close to being straight. So, and that straight is going to be perpendicular to the radius, so therefore tangential to the actual circular path that it is on. So in that case, if we assume that we are making that condition, that our displacement is tangent to the circle at that instant, then when we look at our forces, we're going to need to resolve the forces into components that are parallel and perpendicular to the displacement. Because in order to do restoring force, we're looking for forces that are in the opposite direction of the displacement. So when I look, I have my tension force, My tension force is perpendicular to that little displacement vector that's right there. So because it's perpendicular to, it can't have anything to do with my restoring force. My gravitational force is at an angle. So to handle that, I'm going to resolve that into a component that's parallel, which is this FG parallel over here, and a component that is perpendicular. So we know that perpendicular components to the displacement cannot be part of the restoring force, so we don't worry about FG perpendicular. Actually, FG perpendicular and FT are what are creating the centripetal force. So we could write a centripetal force equation that would be FT minus FG perpendicular. And we could do centripetal force for that. So that is not related to my restoring force. What is related to my restoring force is this gravitational force that is parallel, because if it's parallel to my little displacement on that arc length, then we are going to work. Now, if you look, that FG parallel right there in terms of that infinitesimally small arc length that we're assuming that our displacement has gone through is in the actual opposite direction of our displacement from 0. So we're going to assume that our theta equals 0 is here. So at this point, we are going to assume that my FG parallel is in the opposite direction to theta, because our theta and therefore our displacement along that line are going to be in this direction, whereas my gravitational force is in the opposite direction. So that is true. Now, if we look at this triangle that is made, our FG parallel is going to be the opposite side of that triangle. We have a right triangle right there. So our FG parallel is going to be mg sine of whatever the angle theta is. So I can see that my parallel component of my gravitational force, which is my restoring force, is dependent on the displacement. But here's the problem. We have to have our restoring force directly proportional to the displacement, not the sign of the displacement. So this creates some problems. Well, what we can do is we can go through and set up a differential equation for this. So in this case, our differential equation would come from torque, and that our gravitational force is going to be creating torque, and that torque is going to equal I times alpha. So that gravitational torque is going to be due to that parallel component when we look back over here, because that's where our 90-degree angle is going to be. So our torque is going to be FG parallel times whatever the radius is. Our I for the pendulum bob is going to be mr squared, and our alpha is going to be d squared theta over dt squared. So our FG is going to be mg sine theta. R is equal to mr squared d squared theta over dt squared. Oh, we used L here for the length of the string, so I used R's, but the R's are going to cancel. The m is going to cancel. So we get g sine theta is equal to L d squared theta over dt squared. In terms of the magnitude. Now, there's a negative here, and the negative is because it's actually in the opposite direction, which is kind of nice, but then we get the g sine theta over L. So, because the gravitational force is going to be, the torque is going to be in the opposite direction as the angular acceleration. I just kind of worked with magnitudes in my derivation. I apologize for that. You're not going to be expected to be able to do the derivation on your own. There's a derivation packet for this for you to practice on, and it kind of goes through a little more detail about where that comes from. But this sets us up very similar to what we had for the mass spring system, except for we've got a problem, and that is the sine theta. It's sine theta, not theta. So what we have to do is we have to find a way to make this resemble a little more our simple harmonic motion, because theoretically this really just needs to be a theta. It can't be sine theta in order for it to be simple harmonic motion. So if you have had a course on infinite series, which usually tacked on somewhere in your calculus sequence, Taylor series expansion would give us sine theta is approximately equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus, and it just keeps on repeating in a Taylor series. Well, what ends up happening is if theta is very, very small, then what happens is theta cubed is very, very small, and theta to the 5th is very, very small, because anything that is very, very small squared is going to be even smaller. And so in terms of approximations, our sine theta is approximately equal to theta, according to the Taylor series expansion. So that allows us to replace sine theta just with theta. And then this looks like simple harmonic motion. So when we do that Taylor expansion, and we assume that sine theta is approximately equal to theta, we get the d squared theta over dt squared is equal to negative g over L times just theta. And then this looks very similar to our previous equation, because we had d squared x over dt squared is equal to negative k over m times x. So same kind of idea, which means we can use a similar format of our function. So we can define that a solution to this differential equation is going to be theta of t is going to equal theta max cosine of omega t plus phi. We also know that the general solution, we get that the standard form, of the differential equation tells us that d squared x over dt squared is equal to negative omega squared times x. Same thing is true here, but in this case, we're going to set our omega squared equal to the g over L. So that means omega is the square root of g over L. So if we were to rearrange and solve, we would find that the period of a pendulum is 2 pi square root of L over g. And so this makes sense because the length is related to our rotational inertia. So that way, the bigger the length of the string, the more rotational inertia we have, and therefore the longer the oscillation is going to take, so we're going to have more resistance. Gravity is what's providing that restoring force. So the larger our value for the acceleration due to gravity or the gravitational field strength, the smaller the period is going to be because you're going to be able to accelerate at a faster rate. So really, really similar to the process. We just had to make some weird assumptions with our pendulum because of that small angle. So whenever you are working with a pendulum, usually they'll give a hint and they'll say something like, assuming theta is small, or you should write, assuming theta is small, then you can use this equation. And you can use this equation for our period of our pendulum. So similar things kind of go on with everything. You can find the angular frequency d theta dt. You could find your angular acceleration d squared theta dt. You can do all of that like we did before. and it's all going to be that same cosine function, so we're not going to go through that same whole process again. And then the periods of these oscillations are completely independent of amplitudes. That's something we didn't quite mention earlier, but with the pendulum, we do have to assume theta is small, because if theta is not small, then this is not strictly true. The amplitude does start to matter. So assuming theta is small, the period of our pendulum is dependent only of the length of the pendulum and the gravitational field strength. For our spring, it's dependent only on mass and the spring constant. And here we are assuming that we have an ideal spring, because if you don't have an ideal spring, then this period formula will not work. So what happens to your graphs is if you change the amplitude, the period is still the same. What ends up happening is with bigger amplitudes, you have bigger maximum forces, so you have bigger accelerations. So even though you're going to cover a larger distance, your accelerations are also going to be larger at their maximum, so therefore it'll still take the same amount of time. So when we're looking at our simple harmonic motion, energy is also going to be conserved in order to have simple harmonic motion. And this is an example of the mass spring system, but this would also work with like a pendulum system at a small angle. It also works with some of our oscillators that you will see in physics 2 with like electrons, electrostatic forces, and so forth. So in this case, with a mass spring system, our kinetic energy is 1/2 mv squared. We're going to sub in that our v of t is going to be equal to negative a omega sine of omega t plus v. So basically you square that whole thing, the negative cancels, a squared omega squared sine squared, and you get this equation right here. So we end up with a sine squared function, and then our k max, that would be our maximum amplitude of the kinetic energy, would be equal to 1/2 m omega squared a squared. With our potential energy, we're going to be using x of t. X of t is a cosine of omega t plus v. So when you square that, you're going to get a squared and cosine squared. So we have, once again, a cosine squared function, and then our maximum elastic potential energy is 1/2 k a squared. Now this one you should recognize because we've actually done spring collisions before in conservation of energy. So that should actually look pretty familiar. Now our total energy is going to be E is going to equal to K plus U. And it's going to equal 1/2 k a squared, or it's going to equal 1/2 m omega squared a squared. And so we could actually prove that for a spring, we know that omega squared is k over m. So no matter which one of these equations you're using, if I do 1/2 m times k over m a squared, the m cancels and I get 1/2 k a squared. So this is not just coming from the potential energy, it's coming from our kinetic energy. Now, it's going to be equal to that, and that's because if our kinetic energy is at a maximum, our potential energy is at a 0. So our total energy is going to be constant, and it's going to have a value equal to 1/2 k a squared. This is the easier one to use because then all you have to know is the spring constant and the amplitude of the oscillation. Now, if you were to graph these are going to oscillate a little bit differently. Because they are sine squared functions, what happens is you can never have a negative value. And in the time t that the spring is going to oscillate, the spring goes only through one maximum to one minimum, x and t. So this is our period t right here. But because of the squared, we are going to have to oscillate twice. Because if you think about it, if I square this function for x, basically any value that becomes negative has to become kind of positive. So what ends up happening is when you've got this negative max here, it has to become a positive max. So you end up with an oscillation that looks more like that. So you have to be really careful with this because it appears to oscillate in half the time, but it's the energy is going to it's going to switch back and forth between kinetic and potential energy at a more rapid rate than the actual oscillation. And that's because of the square there. And the fact that our energies can never be negative. So if you were to represent this on an amplitude graph, so this is a position versus energy graph. Our amplitude here and our negative amplitude are there. So you can see when we're at our positive and negative amplitudes, we are all going to be potential energy, and that our kinetic energy is at a maximum when we're at a position of 0. Our total energy would actually be constant. So this energy is going to switch back and forth between kinetic and potential. So that those are going to have to add up to be whatever total energy there was at the start. So we can also have damped oscillations. This is what really happens in the real world. So if I was to put a mass on a spring and let it go, it's not going to oscillate back and forth with the same amplitude forever. It's going to have a decreasing amplitude over time. So that amplitude is going to decrease. So our resistive forces are kind of like air resistance. They're kind of like drag. Most of our resistive forces that we're going to be looking at are going to be dependent on the velocity that we have. It's possible that you could have like a linear friction force for like a mass that is like on a table. And if that is just the friction force, then that is going to be a different model, because that friction force is just going to be F resist. It's just equal to negative B. It's just going to be equal to some sort of constant. You could also have, if you have really, really fast oscillations, as we saw with drag, if you're moving really, really fast, then you can end up with like a B squared model. So this is just one kind of example of what this is going to look like. So we're just going to assume that this is our standard resistive model here. So basically what happens is that you end up with more resistance the faster that it's moving. So that's going to convert energy from the motion into heat, and that's going to cause smaller and smaller oscillations over time. So if we were to include that resistive force into our model, both the resistive force and the spring force would act in the opposite direction to the motion. So subbing in, assuming negative BV, and assuming we have a spring oscillation, we'd have negative BV minus Kx is equal to m times A. V is dx dt. Oops, dx dt. And A is d squared x over dt squared. So now you could sub both of those in. And what you end up getting is you get another second order differential equation. This is actually a quadratic kind of function type differential equation. And so it's actually possible to solve this by doing some differential equation tricks and Euler's method and stuff, which is really kind of fun. But basically what happens, like if this was like air resistance, or in this case, they're putting the bottom of the pendulum bob into like a fluid, you're going to end up with kind of this decreasing amplitude. So if you were to solve this one, or find an equation that solves it, you end up with x of t is equal to a e to the negative b over 2mt cosine of omega t plus v. Way, way, way outside of the bounds of like the course as to how this comes up with. I've done it. It's actually really fun math, like I said before. But the way this kind of works is if you were to look at the equation x of t is equal to a e to the negative b over 2m times t, that actually creates a boundary for the oscillation. So if you were to graph that function and you were to graph the actual motion, then this function right here creates that boundary. And so we have an exponentially decreasing amplitude to that oscillation. So it's still oscillating. The period itself doesn't change because our omega doesn't change. But we create this kind of decreasing oscillation over time. So there are other types of damping. So what ends up happening, like the blue one is undamped. So we have kind of our underdamped version, which is the one that we were kind of looking at. So you're going to have this kind of decreasing oscillation over time. We have over-damped, which means that the resistive force is so large that the restoring force doesn't even have a chance to create an oscillation, and it just decreases rapidly. And then critically damped is going to happen even faster. So you can see the green one just kind of decreases almost immediately down to 0. So kind of different mathematical models depending on the resistive force and the restoring force. Now, there's some other cool things that result from all of this. So just like we can have damping that kind of reduces the amplitude of an oscillation, we can actually create situations in which the oscillations themselves can actually feed and create a larger amplitude. So if there is some sort of forcing, which means the oscillation is being caused by like an external force, if that external force is being applied in an oscillation that is at the natural frequency of the oscillator, what ends up happening is you get larger and larger amplitudes over time. So we can see that we've got a forced oscillator, this yellow thing, that is kind of forcing our spring to oscillate at the exact same rate that would normally oscillate. So kind of like the sum of those oscillations are going to get larger and larger over time. We can also have a non-resonant condition where sometimes the amplitudes are larger, sometimes the amplitudes are smaller. And that's when the forcing frequency is not the same as the natural frequency. So you'll kind of have kind of this decreasing, increasing kind of, it would seem more uncontrolled, but you would actually be able to observe like that there is a pattern in the maximums and the minimums. So there's a cool video that I would like to show.
It opened on the 10th of June, 2000, attracting thousands of people and the media. But as the people poured over the bridge, it was clear something was wrong. The bridge was wobbling from side to side.
I got a phone call midday saying we had a problem. And my first reaction was same as everybody else's. Well, all bridges move a little bit. There's an exaggeration going on. But Roger said, no, this is real. And so I came down early afternoon, and you saw it, and you think this isn't real. This can't be happening.
It was very disappointing. We were witnessing the bridge performing in a way that we hadn't anticipated. We'd done lots of work to try and understand its behaviour. We felt that we understood it very well, and here it is doing something completely unexpected.
The engineers had tested every element of the bridge, from the cables and bolts to how the bridge would behave. Regulations and codes of practice give engineers basic design guidelines. These codes are based on years of experience and look at how different vibrations can affect a bridge. In 1941, the effect of wind-induced vibrations was fully understood after the Tacoma Narrows Bridge in America collapsed under a strong, persistent wind. But it's not just the elements. Soldiers marching can create sufficient vertical vibration to bring a bridge down. Before crossing, they're always ordered to break step.
Break step!
Signs on some bridges still bear witness to this danger. As engineering advances, the bridge building codes are continually updated. Arup researched beyond the requirements of the codes, studying pedestrian vibrations in detail.
With regard to pedestrians, we did a lot of work on vertical vibration. That is, as a pedestrian walks over the bridge or a group of pedestrians, what kind of force, repetitive force, do they put into the bridge?
Arup's calculations followed the codes in assuming that people walked randomly, and the major force they generated was vertical. But on the Millennium Bridge, something unexpected happened. People changed the way they walked in reaction to the movement of the bridge. To balance themselves, pedestrians spread their feet apart, creating a significant lateral, not vertical force. More importantly, the people's reaction was almost identical. everyone stepped the same way at the same time, creating a synchronized rather than random force. The frequency of this force matched the natural frequency of the bridge.
The motion of the crowd was synchronized with the motion of the bridge, and that's actually proved to be a very important observation. We also observed a quite bizarre behavior, that we could control the level of vibration by limiting the number of people, but it was far from a linear relationship. We noticed that it was almost an on and off situation, that either, the centre span particularly, either it was vibrating or it was fine.
The vibration developed when a large number of people picked up the slight movement all lightweight bridges exhibit and locked into it.
Lock-in is the term that we've used to describe the fact that people, as they walk over this moving surface, sense that movement and adjust their gait to take account of it, to stay up, to keep their balance.
Lock-in seemed to be a problem no one had come across before. But Arup then identified two bridges that appeared to have a similar problem. One in Japan and one in France. However, reports of the problems on the Solferino Bridge in Paris were confused, and they did not identify the cause. In Japan, engineers did publish their understanding of the phenomenon, but in a journal of seismic engineering, unlikely to be read by bridge engineers.
The body of knowledge hadn't disseminated beyond those people, and Arabs didn't know about it, I didn't know about it, and specialist checking engineers, who are the most likely people to have known about it, didn't know about it.
As news of the bridge spread, Arup received reports of other bridges of all shapes and sizes that had wobbled. This meant that any bridge with a low natural frequency carrying large numbers of people could begin to sway. Clearly, the phenomenon was not caused by the Millennium Bridge's innovative design.
So, you can mathematically describe some of the different relationships here between the damping force and the angular frequency. So when you take a look at kind of what the driving frequency is omega d, okay, so that would be what's causing the force oscillation. When it's equal to the angular frequency, what you end up getting is you get kind of this peak. So that peak kind of occurs in the same location kind of in most of these oscillations. We can see that when we start getting kind of like to be underdamped, that it's going to be, we're not going to have that peak at all, but that peak is going to kind of shift in the relationship between those. So the more damping you have, the lower frequency that it's going to kind of shift onto. So they can mathematically describe that. I have a couple other videos here that are linked that are related, which are really interesting watches. So if this is something that you're kind of like, oh, this is really cool, this is happening in real life, there's some there for you. I also have some additional tutorial videos that would be really good for you to take a look at. We have some more problem solving examples for what you would do with the equations now that you have them, and so forth, that I suggest you take a look with. Remember, these slides are linked in D2L. All right, have a great day.